Let's talk about depth perception. So the problem here that we're going to talk about today is that the input to the visual system consists of two-dimensional images. Okay? The world is 3 dimensions, and people are pretty good at estimating the 3-dimensional structure. You can hold a shape in your hand, and visually be able to assess the shape. You can tell how far things are away from you, and so on and so forth. Okay? So the extraction of 3-dimensional structure from the 2-dimensional images that the eyes receive is important for lots of things, for navigating through space, for interacting with objects, so forth. And the most reliable source of information about the 3-dimensional structure of the world is visual, at least for humans. Okay. Some other animals use sonar and other things like that. Okay. All right, so the keys to the solutions. One key is the fact that you have 2 eyes. Okay? And we're not going to talk about that in this lecture. That will be for next time. The other key are assumptions that we make about the world that we have presumably learned or internalized over evolution or development, coupled with implicit knowledge of the physics and the geometry of light that comes from objects to the eyes. And so we're going to talk a lot about depth cues. All right? We've talked about cues previously in the class. When you talk about a cue, we mean a source of information. So some aspect of the stimulus that provides information, in this case about a variable that we care about, like depth. Okay? So there are lots of visual cues to 3D shape and depth. Okay? So stereopsis is the one that is best known, but you can see 3 dimensions without it. So if you just close one eye, like the world doesn't really look that different, right? You can still tell that certain things are further away than others, and you can see the 3-dimensional shape of objects pretty well. Okay? So this is a partial list of cues to depth. We'll talk about a whole bunch of these. Shape from shading and drop shadows, linear perspective, texture gradients, familiar size, height in field, aerial perspective. Last time we talked about the kinetic depth effect. There's also motion parallax. Those are depth cues for motion, occlusion, focal blur, and this is not an exclusive list. Okay? So the first thing I want to talk about today is shape from shading. So we've alluded to shape from shading previously in the class, and it refers to the fact that variations in luminance are often interpreted as shape. And the basis from shape from shading is that many surfaces are approximately Lambertian. Right? So we talked about Lambertian reflectance in the context of lightness perception. So a surface is Lambertian if the amount of reflected light is determined by the angle between the incident light ray and the surface normal vector. But the surface otherwise scatters like equally in all directions. And so this is like a picture that kind of depicts this. So the black arrow is the surface normal. All right, so this is a horizontal surface, so the normal is perpendicular to that. The yellow arrow is the direction of the illumination. Okay? And then the little blue arrows are scattered light rays. Okay? And so what you're supposed to take away from this is that irrespective of the direction of the illumination, the light gets scattered equally in all directions. But you can see that the light the most light reflects off of the surface when the illumination is perpendicular to the surface. And as the illumination becomes more oblique, there's less light that's scattered. Okay? So this is the characteristic of a Lambertian surface. All right, and so the basis of shape from shading is kind of like the opposite of what is shown in this diagram. So this diagram is showing a situation where the surface orientation is fixed and the illumination direction is varied. Okay? And that doesn't happen very often in the world. So typically in the world, there will be one light source, and so the direction of illumination will be fixed in some particular direction, but the orientation of the surface will vary because like an object is curved. Okay? And so for a fixed lighting direction, the amount of reflected light will then vary with the surface orientation. And so it follows from that if you knew the direction of illumination, and if you also knew that the intensity changes in the image were only due to shading, then you could infer shape. Okay? And so there are a bunch of classic demonstrations that people do seem to do this under many conditions. So this is a classic stimulus, an illusion, if you will, where the physical stimulus is these circles, and inside each circle there's a luminance gradient. Okay? And it just goes from light to dark or from dark to light. Okay? And so when you look at this, most people will see is a set of bumps and a set of craters. Okay. So does anybody want to hazard a guess as to why some of the circles look like bumps and others like craters? Well,
because you expect that the light is coming from above, so it looks like it would be illuminating, like if it's illuminating from above, then it makes sense that there'd be lightness on top of above that like shading on the bottom.
Yep.
Vice versa for a crater.
Yeah, that's exactly right. So the visual system seems to have a prior that favors illumination from above. So we very commonly, by default, will assume that illumination comes from above. Okay? And so if the illumination was coming from below, then the inferred shape would be the reverse of what it is, right? So the things that are bumps would be craters and vice versa. Okay? So shape from shading is important in art. So bas-relief is a style of sculpture that relies exclusively on shape from shading. So there's some material here, and somebody carved some 3D structure into it, but then all of the luminance variation just comes purely from shape. So it's illuminated from a particular direction, and then you're able to see the 3D structure via shape from shading. You can also see evidence of shape from shading in lots of like real-world photographs. So this is a photograph of a crater, either on the moon or Mars, I forget which. Okay, but it doesn't really look like a crater here, right? So the prior favoring light from above is again at work. So this is the crater. Okay? So it's just flipped upside down here. Okay? So there's lots of examples of photographs of things where if they're taken from an orientation where the illumination is coming from the direction that you don't expect, they look funny. This is one that I just saw the other day that's kind of striking. So this is a picture of sand dunes, okay? But it really doesn't look like sand dunes, right? It looks like a whole bunch of little craters on the surface. So here's the other orientation, and you can see the correct 3D structure. Okay. This is a really pretty awesome demonstration of the same thing. So this is a physical thing that was actually like engineered. So there's some 3D shapes that are embossed into this thing, and then it's lit from a particular direction. Okay, but it's on this table that can rotate, and so when you look at it now, it kind of looks like this is sticking out, right, and this is sticking out. Okay, but whoa, now it flips, right? Okay, but it's going to get even cooler. So now they're going to pour some liquid so you can kind of verify which parts are actually sort of the valleys, right? Okay, watch closely. Yeah, so you know that the places where the liquid is present are kind of indented in the surface, right? But your priors on the direction of the illumination are causing you to misperceive the shape from shading. Right? So again, a great example of how perception is kind of encapsulated and sometimes cognitively impenetrable. Okay, so that's shape from shading. So again, key principle of shape from shading. It works for Lambertian surfaces. Really, the kind of most straightforward way to infer shape from shading is to know or assume a direction of illumination. Sometimes we assume the wrong direction of illumination, so you get the shape right, shape wrong. And critically, you have to also assume that the intensity variation is due to shape rather than due to, say, paint, right? So in these this is actually something you could print out on a piece of paper, and so the intensity variation here would be due to paint, and so you misperceive things. Now, in the real world, like things are actually much more complicated because shapes often do have like reflectance variation on it, and people are actually pretty good. You know, if you take an object that has reflectance variation, you're pretty good at actually correctly estimating the shape. So your visual system has this amazing ability to actually kind of separately infer the contributions due to shading, the contributions due to reflectance, and that's kind of a little bit beyond the scope of what we're talking about here, and not terribly well understood, but remarkable. Okay. Another very powerful cue to depth is shadows. Okay, so this is just a display that has a few shapes, and you can see that like some are in front of the others, and you can tell that this occludes this and this occludes this. Okay, so there are these occlusion cues present here, But then when we add shadows to the display, these are typically called drop shadows, okay? You now actually see the objects as being separated in depth, right? So shadows are a very powerful cue to depth. The visual system, so typically in the real world, they are caused by one object occluding the illumination, so blocking the illumination. And so the region of a shadow is typically dark in the image, okay? And so the visual system seems to have internalized that regularity, because when you artificially make the shadows lighter rather than darker, and you can do this in graphics programs, then you don't get the sense of depth, right? And what does this look like to people, actually? What's that?
It looks like the inverted image, the casting white shadows.
Yeah, or like spray paint, kind of, right? To me, it looks like somebody took a can of spray paint and sort of sprayed it, right? So again, like, really doesn't have the same effect as a shadow doesn't look like one. And if you just invert the whole image, then it also doesn't really produce the sense of depth. So shadows have to be dark. In computer graphics programs, you can kind of play around with both shape from shading and drop shadows. And these things, again, they're happening all the time in the world, and you typically are not, you just don't even really notice them, right? So this is just a picture of eggs. And in this case, it's pretty obvious that the eggs are sitting on a table, right? Because you get these kind of shadows that suggest that the eggs are sitting on the table and blocking the light. If you remove the shadows, the eggs kind of look like they're floating in space in front of the table, right? But if you get rid of the shading, so you just color all of the eggs white, now you lose the 3D shape, right? So normally, like, you sort of look at these eggs and they all just look white, right? So it's like your visual system is kind of separating out the contribution of the shading from that of the reflectance. And remember how when we looked at the Retinex algorithm, when we ran the Retinex algorithm on an actual image, Retinex would make the mistake of actually interpreting some of the shading that's due to shape as being due to illumination, right? Because Retinex assumes that all of the gradual variation in luminance is due to illumination, right? Which is not a correct model of the world. So there's lots of luminance variation due to shading. So the visual system is really sensitive to the relationships between the positions of shadows and the depth relationships of objects to the surfaces on which they sit. So the drop shadows kind of have to align correctly for an object to sit on a surface. So you remember in the very first class, we showed this demonstration of a ball that kind of rolls across the screen, and depending on the trajectory of the shadow, you see these very different 3D trajectories. And there's lots of these really cool, I kind of collect these images where just sort of by accident, the shadow's kind of in the wrong place, and then it sort of causes things to look like they're levitating. So this is a situation where I guess there were like a lot of flagpoles on this particular beach, and there's one that just happens to be casting a shadow. The person's sort of standing on some platform on the sand, and the alignment of the shadow and the surface are good enough that the person looks like they're kind of floating. Here's a situation where there's, I guess, just some dirt on the ground that kind of happens to be in approximately the right place and like approximately the right color to plausibly be a shadow, and so causes the trash can to float. This is a cat with supernatural powers. Again, same kind of thing, just a sort of dark patch in the right place. You can also get some pretty funny instances of this involving water, because the shadows will be cast on the bottom of the ocean in this particular case, right? And can cause the boat to seem like it's sort of floating. This is another one that I came across where the particular angle of the sun causes the shadow to be in a place where you can kind of see the train is sort of floating. So you start looking at these things and you see them all over the place. So shadows are caused by the geometric relationship between an object and a light source. Okay? And so when you're using the shadow to infer depth, you're kind of implicitly taking advantage of that relationship, right? So the visual system is like internalized something about the relationship between light sources and objects and shadows. And so you might imagine that what happens is like you actually are building or you're inferring like an entire scene layout in your head, right? Where there's a light source in a particular place and shadows that are cast relative to objects. And that doesn't actually seem to be what is happening. So this is kind of an interesting demonstration where you get pretty good depth from the shadows in the top two circles of circles. Logically, like that display sort of doesn't really make sense, right? Because you can kind of tell from the direction of the shadows relative to the objects that in this case, the light is kind of coming from the upper left, right? In this case, the light must be kind of coming from the bottom left, right? For the shadows to be where they are, right? And so you couldn't really actually generate an image like this without some really contrived setup with two sources of light that were only cast on part of the scene, right? But it doesn't seem to bother you, right? On the other hand, down here, where the positioning of the shadows has kind of been randomized locally, that really seems to kill the sense of depth for the most part, right? So there's some degree of kind of local consistency that is really required for this to happen, but it doesn't seem like you're kind of modeling the global scene, okay? And this is like, we've seen some other hints of this so far in the class. Like remember when we were talking about lightness illusions, we saw evidence that people weren't really modeling a full kind of global version of the scene. There's sort of more local kind of mid-level stuff going on. Any questions about shadows? So another regularity that influences depth is the geometry of the geometrical relationships between where objects are in the world and where they project on the retina. And so very often we're standing on a ground plane, and so things that are further away from us tend to be on the ground plane. And so things that are further away tend to be higher in the visual field. And so you can get these effects like this. And they also, as things move are further away, they also tend to project smaller images, okay? And so you can get these effects. Like, so the one on the left gives like a pretty compelling sense that the surface is receding in depth, okay? Because the objects get smaller as they go up in the visual field, right? That's more or less what would happen in a typical situation in the world. The one on the right has a much weaker effect, right? Because it sort of violates that geometric regularity that is sort of typical of what you would observe in the world. Okay? So again, the common theme here is like the visual system has sort of internalized the regularities of the world and uses those to solve this ill-posed problem of depth perception. And so this is an example it's kind of an example of a texture gradient in the sense that you have all these repeated elements and the texture changes in some systematic way that's kind of consistent with something receding in depth. And those are actually super common. So here's, this is a case where an artist decided to kind of trick the visual system. So this is sort of a funny pattern that got painted on a perfectly flat floor. But instead of interpreting this as what it is, which is a flat floor that's got sort of a weird warped texture on it, right? You infer a situation where the depth is kind of where the shape of the floor is kind of curved, right? And the texture is uniform and just pasted on the curved surface. So of course the inference is ill-posed, right? And so you've got to have priors to constrain the inference. In this case, the prior is that the texture is uniform because textures in the world tend to be uniform rather than having the weird kind of modeled shape. Okay. Here's another pretty cool example of the same kind of thing. All right, so texture gradients are another really powerful cue to depth. Okay, another very important thing that is related to depth perception is what's called Emmert's law. Okay, so Emmert's law describes the relationship between the size that we perceive things to be, the distance that we perceive them to be away from us, and the visual angle that they subtend. Okay, so the idea is shown here, right, which is that you can have two objects of different sizes, and if the big one is further away, it will subtend the same visual angle as a small one that's closer. Okay? So there's this relationship between visual angle, inferred distance, and inferred size, right? Because in the actual world, there would be a relationship between visual angle, distance, and size. And so there's lots of these instances where either you know how big something is because it's a familiar object, okay, and so that you use that to infer how far away it is, or you know how far away something is and you use that to infer the size. All right, so we're going to do an experiment to verify this. And so this experiment is going to involve staring at one of the lights in the ceiling, okay? So you're going to do this for, I think, like about 30 seconds. So kind of get kind of close to a light and kind of look up at it. And the purpose of doing this is we're going to kind of burn a temporary after image into your eyes, okay? And the reason that we're doing that is that when you generate an after image in the eye, right, that's covering some fixed portion of your retina, right? So it corresponds to a particular kind of visual angle that would normally project onto the retina, all right? So the idea is that after you stare at this thing, you're going to get this after image. It's going to have a fixed extent on your retina. So now what we're going to do, all right, hopefully you got a pretty good after image. So now I want you to look at your hand, okay? All right, so that's going to be some particular size. Now, take your hand down and look at the wall, okay? And the thing should look a lot bigger. You might have to keep blinking to kind of get the after image to restore itself, right? All right, so what we just did is we generated a stimulus of fixed extent on the retina, okay? But you can cause it, so now I'm like looking at it on the back wall, and that's enormous, right? So you can cause it to look different sizes by looking at things at different distances. And so that it seems to be the case that the visual system assumes that that retinal stimulation is due to something that happened at the surface that you're looking at, right? And so you look at something that's close, and you assume that the thing is small. If you look at something that's further away, you infer that it's large. Yeah.
Why does blinking cause it to come back?
Oh, it just kind of it's refreshing the adaptation. Yeah, so you're kind of temporarily bleaching the photoreceptors, and like I think probably what's happening is that there may be some downstream adaptation that you then kind of like reset with the blinking. Yeah. So you're just sort of making the after image visible again. Yeah. I don't know the exact mechanism actually. Okay. So Emmert's law, right? So the relationship between how big things look and how far away they seem. Okay. So that's one example of this. Okay? And it's a pretty good party trick. And you see Emmert's law in like lots of different settings, right? So here, this is a situation where the big balls look a lot closer than the small balls, right? So this is a case where the visual system seems content to assume that the objects are all the same size, and thus the changes in size are attributed to differences in distance. Okay? Here's a situation where you know the relative size of these body parts, right? You know that hands are of a certain size relative to somebody's face, and so the fact that the hand is bigger in the one on the left leads you to conclude that it's a lot closer. Right? So again, hand looks closer, and this all kind of happens implicitly. And so again, if you look around, you can kind of find funny instances where this sort of plays some tricks on perception. This is kind of an interesting photo that I came across where the girl in the middle kind of looks like she's floating, okay? And so I think the reality is that she's a lot taller than her brothers, right? But your visual system sort of seems to assume that these things are all probably the same size, right? And thus that the girl has to be closer than she actually is, which means she's floating in the air, right? Something like that. Here we got some really big pigeons. Okay. So this is a kind of a funny photo. Can anybody tell what's going on here? Yeah? Yeah, but you kind of don't notice the ledge at first, right? So it sort of looks like they're right next to the car. So if you assume that the cars and the birds are at the same distance, then they're about the same size on the retina, which means they're about the same size physically. So you got giant pigeons. All right, Emmert's law. Any questions about Emmert's law? So in some cases, the size is unambiguous, and thus that kind of determines the apparent distance. In some cases, the distance is less ambiguous, and that will determine the size. Yeah?
You think we have bias for light stronger
do we perceive this as large vision and not small time?
Yeah, I think it's a good question. Yeah, I don't know the answer to that, and I'm not sure that it's completely known. And you know, I mean, you might imagine. Well, most of us have a lot of experience with toy cars, right? So you might think that it could be the opposite. Yeah. No, I think the absolute size of these things is sort of, it's interesting that you anchor with the car rather than the pigeon. Okay, another cue to depth is aerial perspective. So in general, things that are kind of further away are more blurry because as light travels through the air, it gets scattered, and things also tend to look a little bit more bluish. And so you can see this oftentimes in photographs. This is a photograph of a beautiful landscape, and the stuff that's further away is lower contrast, blurrier and a little bit bluer. So again, it's like a regularity of the way that optics works that we seem to have learned. Another really important depth cue is linear perspective. Okay, so linear perspective is due to the fact that lines that are parallel in the world will generally converge in the image, okay, unless they lie in a plane that's parallel to the image plane. Okay, so if you have lines that are in a plane that's parallel to the image plane, those will remain parallel in the image. But if they're not in the image, they will converge. Okay, and so you can see in this particular case, this line and this line are a good example of that. Okay, or like that and that. Right? Okay, so the question is now, how do we know that lines are parallel in the world? Right? In principle, these lines might not be parallel in the world. Right? And that's. Does anybody have an idea? Why are lines parallel in the world? What would cause things to be parallel? Humans, yeah. I think that's one possibility, yeah. Maybe also gravity, you know. But yeah, like people like to construct rectangles, you know, so there's like a lot of things in human constructed environments that tend to be parallel. Okay? And so this is a classic illusion where depth from both linear perspective and from texture. So again, we got linear perspective, so these lines kind of are converging. Makes it look like that's a lot further away than this. There's sort of a texture gradient. Okay? And what's cool about this is that it looks like there's a really big monster chasing a smaller monster, right? But in fact, the two monsters are exactly the same size in the image, right? So this is, again, Emmert's law, right? So you've got the same visual angle being subtended by this monster and that monster. The depth cues indicate that this one is further away than this one. Okay, so Emmert's law tells you that this has got to be proportionally bigger than this one. Here's another kind of cool example. So we got two cigarettes, okay, and they're positioned on a drawing that is making use of linear perspective to cause this to look like it's closer to you than this, right? Two cigarettes are physically the same size, and thus they're lying on a table, right? So they're the same size on the retina, but they look very different, right? This is a thing that I just saw that's kind of interesting. So check this out. See if you can figure out what's going on. So this is a artist who's drawing this thing. It's going to look pretty 3D. Now he's going to jump. Okay, notice that like the artist has changed in size, right? Okay, so it looks like this person is changing in size. Anybody want to try to explain why the person looks kind of small here and bigger here and very big there? Yeah.
He's getting like physically close to the camera, but he is because he's strong. Like he's just bringing down.
Yeah. Yeah. So in reality, this person is jumping horizontally by a pretty big distance, right? So the distance of the camera is changing. You are misperceiving this person as actually kind of jumping up and down vertically, right? So, and that if you assume that the distance is remaining constant, then the person's got to be changing in size. Okay, so in this case, like the depth cues here are so powerful that they sort of overcome the presumably strong prior you have that like people stay the same size, right? Okay. All right, so another kind of point I want you to take away from this is that we see in 3D, right? So what you perceive is your inference of the three-dimensional structure of the world, right? Now that is derived from these two-dimensional retinal inputs, and it's very difficult for you to actually counteract the visual system's recovery of 3D shape. All right, so this is a classic demonstration that was constructed by Roger Shepard, who's a cognitive psychologist who also kind of was an amateur artist, and so he published a book of these illusions that he came up with, and this is probably the most famous. And so the illusion here is that the parallelograms here and here are physically the same shape, okay, the same size, same shape in the image. Okay, yeah, you're shaking your head. You don't believe me, right? Yeah, it doesn't look possible. Okay. So here's one way to think about, to see this, right? So this is the image kind of rotated and overlaid. You can kind of see that they're actually the same. Here's another animation. Okay. Yeah. But it's really kind of hard to believe. And so the idea is that like these two different shapes in the image look like kind of different shapes in the world because the tables are kind of oriented differently and angled differently. And you infer these, so you're inferring these different 3D shapes in the world, and it's really impossible to access the 2D shapes in the image. Yeah.
Maybe this is another illusion in the image, but is it relevant that the parallelogram seems slightly askew? Like the bottom of the table, of the long table doesn't look parallel to the top of the long table to me.
Yeah, it doesn't to me either. And but this one doesn't quite look exactly rectangular either. Yeah.
Same with like.
I don't think that's important. I think that's just another version. I think in the original version they actually they look pretty well matched, right? Yeah, but the point is that like, you know, so this distance in the image, right, this is the same as this distance in the image, right? But when you look at it, it looks like it's a much greater distance, right, because of the foreshortening effect of projective geometry, right? So you have this thing that's getting projected onto an image, and you're inferring the three-dimensional shape in the world, that overcoming that projective process or inverting it correctly. Okay, so that's kind of an important theme. And then the thing that we'll end with here is this issue of ambiguity and bistability, right? So like one of the amazing things about perception and vision in particular is that we're constantly solving these opposed problems, right? So three-dimensional interpretation in the world in particular is always ambiguous, right? Especially if you kind of look at the world with one eye, right? So there's like lots of different possible three-dimensional structures that are consistent with the image that you observe. But usually we see the one interpretation that is apparently deemed most likely by our visual system, right? So vision is typically quite stable. But sometimes, especially in these more kind of impoverished displays that we often make use of in perceptual science, there are multiple interpretations that are equally likely, and the percept is bistable. So this is called the Necker cube. It's like a wireframe cube. So if you just look at this one on the left, you'll be able to see it in two different orientations, right? So one orientation is that this square is out in front. The other orientation is that this square is out in front. Okay? And they're those are both consistent with the image, and if you look at it, your percept will kind of flip from one to another, maybe every 5 or 10 seconds or something like that. Okay? Raise your hands if you've seen it flip. Okay. Almost everybody. Yeah. And so there are lots of famous examples like this. So this is kind of combining two famous illusions. In this particular case, the face can be seen as an older woman from the side or a younger woman kind of from the back. Okay? And this person is holding their hands up in a silhouette, and that's the duck-rabbit illusion, right? You can see it as a duck or as a rabbit. Okay? So this is a cartoon that I saw recently. So the bartender says, "Can I see your ID?" "Wait, never mind." "Wait, yeah." "I need to see your ID." "Wait." Constantly switching between these interpretations of someone who's underage and someone who's overage. Right? Okay. And so this bistability, we had a question about this last time, right? Bistability is super interesting, right? The fact that you don't get stuck in one interpretation. And one idea is that this is a situation where the posterior, so the probability of the world given the stimulus, is multimodal, right? So there's sort of multiple interpretations that are both probable, and maybe your visual system is sampling from the posterior, so that you sometimes see one thing, sometimes see another. Maybe it relates to adaptation, and what happens is you see one thing, and so some neurons kind of adapt, and then the other interpretation kind of ends up getting favored in some way. Could be potentially sort of due to implementation constraints. We don't really know. But it's fairly prominent. And then these are some other examples of bistable things analogous to the duck-rabbit illusion. All right, let's end there. So next time we'll resume talking about monocular depth cues, and then we'll get into stereopsis, how you derive depth information from having two eyes.